this section of the video, I am going to instruct you to pause frequently in order to do some calculus, or at least algebra, right? Whatever it may be. Because this is a thing where you have done math, which is just like this for RC circuits, and also for that matter for drag forces. And you probably need the practice making sure that you know how to do it for inductors. And it's going to help you with RC circuits, and for that matter also with drag forces on the mechanics exam, because the math is the same, right? It looks like first order drag, right? That's what it looks like. All right. The first thing would be if they ask you to find the current as a function of time when the switch is moved to A. Right? That's a very common thing for them to ask. Or if they simply say something like, write an equation using Kirchhoff's laws to determine the EMF produced by the inductor. Right? That's another common thing they're going to ask. I forgot how that sentence began, but what we're going to do is write a loop equation. That's what you always do with any kind of a circuit, is you write a loop equation. All right, so here's the path my current is taking. There's only one possible loop in this case because B it's not hooked up to anything yet, so we're not concerned with it. So here's my loop. And you should probably be able to see there's three things on that loop. So therefore, my loop equation will have three terms. Those terms are the battery, the resistor, and the EMF produced by the inductor. What the heck is that? It's this equation. All right, now I think it's probably important at this point to note I'm technically being redundant with the negative sign here, okay? I might say plus or something like that, but ultimately it's, for this scenario, going to be minus. The inductor is going to be opposing the flow of current. It's stealing volts, all right? All right, so I'm just going to plug in L di dt for that. All right, now where this becomes a differential equation that you can solve to get current as a function of time is right here. Look at what we got. We have current, and then we have rate of change in current. That's a differential equation if I ever saw one, and this is going to solve exactly the same as like a first order drag scenario. So this is the first point at which I'm going to say pause the video and then resume once you think you've got the equation derived, or if you need a little help with the algebra so you can look at the steps, all right? So on my end, I'll pause, resume after I've done a little bit of algebra, but you should be able to fairly quickly pause it, play, and then it'll skip from one step to the next every couple of seconds. All right, so pause, do the algebra and the calculus, get to an answer which is current as a function of time for this circuit. All right, at this point I would like to note that you have to make sure to plug in bounds. I already did plug in bounds on the left, right? Integrating dt to t, plugging in t for the top bound and 0 for the bottom bound. I didn't feel it necessary to write -0 on this side. However, because we integrated this to a natural log, plugging in 0 does not give you a result of 0. So you do have to plug in that bottom bound of 0. Also, sometimes people forget about this because of chain rule, or don't remember that this is here because of chain rule, but that's there because of chain rule, the 1 over r. Due to the r being with the I up there in that equation. All right, and there is our answer for the current as a function of time for when we move the switch to position A. Okay, all right. the final equation that we get looks like, you know, any natural growth curve that you've seen before, right? The current is going whoop as a natural growth function. They all look like 1 minus e to the stuff. All right, now, because this is of the same form as every other natural growth equation that you've seen, you could probably guess at this point that there would be a thing in here which we could call a time constant. And indeed there is. Now, the format for anything with a quote, time constant in it is always e to the negative t over tau, where tau is your time constant. So that means that tau is L over R. Not R over L, right? Because the format for where the time constant is always T over tau, because the time constant must have units of seconds so that T over tau, the units of seconds, cancel out. Okay? So therefore, the time constant isn't R over L, it's L over R. Okay. All right, so that's the time constant for your LR circuits. All right. If we're moving the switch to position B, then the derivation looks a little bit different. So now we're going to move the switch to position B. So again, you can pause the video and see what you think about the derivation. But again, remember the reason why there's going to be any current when you move the switch to position B is because of the inductor's property of opposing the change in current. If I made this into a graph, right, we already said it's going to be a natural growth curve, right? Meaning initially the inductor is like, no, what is this current stuff? And it won't let any current pass through. As the battery convinces it to let some current through, right, then there will be current and a decreasing rate of change and therefore decreasing opposition on the part of the inductor until you get up to this steady state. Well, then we go and we move the switch to position B. And the inductor has now like had its legs kicked out from under it, so to speak, right? The battery's no longer there to push current through the circuit. The inductor, however, is going to be upset with this sudden rate of change in current, and it is going to produce this EMF in order to keep the current flowing. Okay, all right, so move the switch to position B, write a new loop equation, and then see if you can go through the whole derivation, all right? The way I'm going to conduct this one is I'm going to pause me. I'm going to do kind of like before, write a couple of step-by-step, but not quite as broken as I did it. All right, so pause, do it on your own. And there we have it, an exponential decay function. All right, now the last thing that I'm going to discuss in this video is going to be a contrast that we're going to make between RC circuits and RL circuits, because they actually do operate in kind of opposite ways. And sometimes the AP likes to give questions where they're like, here's a circuit and we put a capacitor here and then tell us some things about it. Now, then we replace the capacitor with an inductor. What's going to happen now? And so you need to be able to basically compare and contrast those things, usually in the form of a graph. All right, so here's the big difference. If you have an inductor in a circuit, the inductor opposes a rate of change in the current. So initially, the inductor will not allow any current to pass through it. Therefore, if I make a graph of current as a function of time, I get that natural growth curve. Now, Mr. Errico, I remember there's also a natural growth curve with capacitors, right? So this right here is for your inductor, current versus time, all right? For capacitors, there was this graph of charge versus time, or volts on the capacitor or something like that, okay? If I made a graph of charge on the capacitor as a function of time, that is a natural growth curve, right? So that's where you saw the natural growth. However, for a capacitor, like if I said this is a capacitor now, for a capacitor, the moment when you have the maximum current is right at the start, when there's no charge on the capacitor. So I will now magically morph this into a graph of current through the capacitor as a function of time. If I made this be a graph of current in the capacitor, you may recall that what that looks like is pretty much the polar opposite of that. It's exponential decay. As the capacitor charges, it permits less and less current to pass through because its opposition to the flow of charge increases as the charge on the capacitor increases, right? So the capacitor makes more volts to oppose the battery as it charges up. The inductor works the opposite way around. The inductor at first is like, whoa, what's all this current stuff? And then a long time later is like, whatever, let the current through, right? So they do opposite things as regards the current. For that matter, if I made a graph of volts as a function of time, those would also be opposites for these two things. If I say volts on the inductor, initially the inductor is like, no current, please. And so it pushes back really hard with a lot of volts. However, a long time later, when we've reached the steady state, it's like, whatever, and doesn't do anything. The capacitor is the exact opposite. Initially, when the capacitor is uncharged, it can't do anything. It doesn't have any charge on it, so it doesn't have any volts on it. However, a long time later, when it is fully charged, the capacitor does not permit any current to flow at all because the capacitor is full. It pushes back with as many volts as needed in order to make the amount of current flowing be zero. All right, so please note that they will ask you, odds are pretty good, to compare and contrast inductors and capacitors, and the easiest way to summarize the contrast between those is to look at graphs of things like current through one, current through the other, or volts on one, volts on the other. All right, so make sure you understand that relationship. All right, I'll see you guys in class, and in class we will discuss more about RL circuits, and we'll get some practice with working out some of the more difficult